So nuclear physics is going to be basically we have two chapters in your book for nuclear physics. The first one basically discusses about the basics, fundamental of particles, right? What are atoms? What are electrons? How was it discovered? Then how was the structure of atom analyzed, right? We learned some about some experiments, structure of model, and ions, isotopes, so on and so forth, right? And then the chapter number two, which is the part of your nuclear physics, starts with basically the radioactivity, right? That is how many type of radiation do we have? We have alpha, beta, gamma, right? What sort of decay is that, right? How does that happen? What is an alpha particle? What is a beta particle? And what are gamma particle, right? You learn about nuclear reactors, that how does nuclear reaction takes place, fusion, and I guess yeah, that is basically it. So let's start with the lecture here. Uh, so first of all, starting with the atom over here. Okay, so let's first of all start with the theory here. What are they saying briefly, and then we'll start with the discussion. Right. So the if you recall, if you go back to the past, right, when electrons, when the nucleus was not discovered, right. So we had an idea of plum pudding, right? We had this idea of plum pudding model here, right? That was just imagine if you have a sort of a dough, right? And you roll it on, you have a plum, right? Pudding. So we basically assumed that we have a plum pudding sort of entire positively charged pair, right? Uh, in which we had basically sort of if we have, let's say, sprinkles all over the pudding, that was the electron, right? So you can assume that you had a pudding here like this, and all the sprinklers on the top were basically electrons, right? So this was the initial model of atom over here, right? And obviously it is not true, which we have learned in this particular model world. Obviously we had no technology advancement at that time, so you're not able to see that through a naked eye, right? Because it was pretty small. Now we have microscopes, we have which can zoom in 2 nanometers, okay, and femtometers, so on and so forth. Then it was basically then the story started, right? That how did we discover the actual model of atom which we have right now? That we have a nucleus, right? We have a nucleus at the center, which we have. I believe if you're taking chemistry, you know about this. We have a nucleus at the center which contains neutrons and protons, right? And then we have shells over here, right? Which contains basically electrons. So in the first shell, we can have only 2 electrons, and from the second shell onwards, we can have eight electrons. Right? So this is the actual model which basically is discovered right now. So we learned the process of how was it discovered, right? By investigating radioactivity, the physicist basically this is Rutherford over here, who basically did the experiment. If you recall the goal for experiment, if you have watched any video or had discussion in your school, so he basically first of all the nucleus was discovered over here, right? That nucleus was not in the entire sort of a pudding, right? It was just a very small part of the entire atom over here. So he did what? He basically took alpha particle, right? So what are alpha particles? I'm going to briefly introduce to them because they will learn this in detail in the coming slides over here. So alpha particle, just assume that they are positive particles, right? They're positive particles. He does know this at this particular point, right? So he did what? He basically took a gold foil and assume that this is a gold foil here, right? It's a gold foil, and he basically did basically what? He passed a sort of a beam, a ray of alpha particles, which is basically going to strike on the gold foil over here, right? So something happened, something interesting happened over here, right? That is going to be as follows. That I can see that most of the particles went through, right? Most of the particles went through, right? Only a fraction of it basically bounced back. Okay, you can see that one ray is basically bouncing back. Okay, and a substantial amount of basically rays were basically deflected in the opposite direction at a particular angle over here, right? So he had a alpha particle source and he had a vacuum chamber, right? So this was completely vacuum over here so that we don't have any radiations of the surroundings in the particle. And we have radium in lead box, okay? So radium is a source of radium is basically an element which generates alpha particles, okay? And we have a lead box wire so that it cannot escape. The alpha particles are harmful for the humans if you expose to a huge amount of alpha particle, right? So we have a lead box which basically absorbs the alpha particles. It does not allow them to go outside, right? Basically blocks it, right? Then you have a notable microscope over here, a rotatable microscope over here. Basically, the other part was basically observing the entire thing using a microscope, that where are the alpha particles landing up, right? So we had a zinc sulfide screen here, right? So what is zinc sulfide? It basically glows when the alpha particle hits on the screen, right? So that is how the scientist was able to see that we are having a particles basically hitting the screen over here. That means that some particles are bouncing in at a particular angle over here, right? So what was the ideology over here? Okay, what happened? So as I told you guys before, that alpha particles are positive particles, right? Right. And if you recall, कि if we have a nucleus, उसके अंदर we have proton and neutron, right? This is the nucleus here. And you know that proton are positively charged, right? And neutrons are basically have zero charge, right? They are neutral over here. So most of the rays, basically, let's basically see okay, what are the observations in this experiment, right? What are the observations in this experiment? So first observation is that okay, most of the rays passed through the screen, through the gold foil, right? And the second observation was that a few ray rays were deflected by certain angle, right? And what is the third observation over here? That uh, very few, could say that ray bounced back, right? So these are the observations which basically the scientist who basically was doing the experiment over here, that was Ernest Rutherford made over here, right? So by just observing this, we can also conclude something over here, right? We can deduce okay, what is happening and why is it happening over here, right? So we had done the experiment. Now we know what is happening over here. Now it's time to conclude, right? Okay, what is the result over here? Why is it happening, right? So the conclusion for the first one is that you can see that most of the rays pass through. That means that nucleus occupies a small, you can say, section of an atom, right? That makes sense, right? It is the smallest, it's pretty small at the center, and most of the area is basically empty over here in a atom over here, right? And what is the second conclusion from the result? That few rays were deflected by certain angle. I'm talking about these rays, right? They have certain angle. Not I'm going to use theta over here. You confuse them with alpha particles. ठीक है? They have certain angle over here, right? So we can say that, and if you recall, कि if we bring a positive charge close to a positive charge, they basically going to repel, right? So the second observation basically conveys the message that nucleus is positively charged. That makes sense, right? We have only neutrons and protons inside the nucleus, right? What about the third observation? That only single ray bounce back, right? The third basically leads towards this particular conclusion that nucleus is pretty is basically heavily tensed, right? What do I mean by that? It occupies a very small volume, but if a particle hits straight towards the nucleus, let's say this is the nucleus here, right? If the alpha particle is coming straight towards this particular nucleus here, it's going to bounce back, right? It's not going to allow this particle to go through, right? Okay. So it is pretty dense over here, right? It's pretty dense. So these are the basic experiments which he did, and these are the observations and the conclusions over here, right? So then the first, basically the term came in Greek time, right? This is basically a Greek term over here, atomos, right? So they used to call the smallest particle known to human history as atomos, right? So right now we know them as atoms, right? Okay. So this is basically T here. So let's see what are they saying here. So this is the same result which we have discussed over here. Yeah, these are the conclusion uh, of this is the conclusion of basically the scientist which was Ernest Rutherford over here, right? So let's see what was deduced over here. They found most of the alpha particles were undeflected, that is, they went through, right? Some were scattered by appreciable angles, okay, and a few, that is 1 in 8,000, bounced back, right? So we have three observations here, which basically uh, explained before, okay. To explain this, basically Rutherford again proposed a new model of atom, right? Okay, how should the actual model of atom look like, right? It's not a plum pudding, okay, with electrons as sprinklers on top, right? So he basically developed a nuclear model of the atom, which in which all the positive charge and most of the mass of an atom formed a dense core of nucleus, a very small size compared with the whole atom, right? So basically, if you recall this particular structure, is getting formed here, right? This one. So you're going from here till here, right? So this was experiment which basically made us realize that the actual form of atom is not a plum pudding, right? It's on the right hand side. Okay. Then yeah, these are just basically this is a zoomed in version of the experiment, right? So this is explaining why that was happening over here, right? So we have particle one, which basically is not hitting any nuclei. It is basically passing through the spacing over here, so it's closed state, right? Then we have particle two, which is basically deflected by a certain angle because it is close to the nucleus here, right? Which you can see here, right? It's passing through closely. And then we have a third sort of particle which strikes directly towards the nucleus, so it bounces back, right? It bounces back. Okay, because positive repels, right? And this is the particle three that is violently repelled by it. It rebounds basically after having a head-on collision here, right? So head-on collision क्या होता है basically? When two bodies strike together, almost their center basically meets the center of the other particle, right? They strike in a linear direction, right? Okay. Now we have seen this. This is a zoomed in version of what is happening and why it was happening before, right? So now this is the model which basically was developed here, right? And shortly after Rutherford proposed his nuclear model of the atom, then Neil Bohr basically worked on to basically explain that how an atom basically emits light here, right? So now they know if you recall that we have tube lights, right? We talked about the tube lights, right? Which basically glows when providing the voltage. Okay, contains some gas which basically glows when we have electricity flowing through them. So basically, when the voltage is when the tube light turns on or you turn on the switch, you basically provide electricity, and electricity basically provides energy, right? So when you given energy, so some elements glow, right? So now, since we have a defined, finalized, basically model of electron, now Neil Bohr was basically working upon what is happening actually inside the atom, which is basically making it glow, right? So what was his basically reduction? Okay, he said that the electron circles around the nucleus at high speeds. Okay, and they maintain a certain orbit, right? Some are basically at the first shell if you're taking chemistry, some are at the second shell, some are at the third shell over here, right? So the closer the electron is towards the nucleus, so the stronger the electrostatic force of attraction is. Okay, and it is difficult to basically take out the electron. Okay, let me like give you an example here. Let's say if I want to basically this is electron one, electron A here, this is electron B here, right? Electron A is close to the nucleus here, right? So they have very strong force of attraction because nucleus is positively charged, electron is negatively charged, and it has very small spacing between them, right? So it has a high force of attraction, okay, as compared to electron B, right? Because it is further away. It has force of attraction, but it is weaker compared to electron A. If I want to take out electron A, I will have to give in more energies compared to electron B. Right? You can basically go back and rewatch the statement here. Okay, it should make sense. Because if we have greater force of attraction, we want to break that bond, right? We have to give in more energy, right? Okay. So, what did he basically thought about after basically deducing कि हमारे पास structure of atom looks like this? He basically thought about the solar system, right? If you recall solar system हमारे पास, ये how does it basically is? It is basically a sun at the center, right? And then we have planets surrounding the sun, right? We have we have Mercury, Venus, Earth, Mars, Saturn. Yeah, we have Venus here, and so on and so forth, right? And Mercury and basically Venus are rotating around the sun here, right? So there is always a pattern in nature, right? So nature basically is a sort of contains a pattern which basically is pretty common in everything, right? If you zoom into your eye lens, your eye also basically takes a pattern of a solar system, right? If you look at the nucleus at the atom using a microscope, it also basically contains something at the center, and the electrons are rotating around the nucleus here, right? So he basically pictured atoms as miniature solar system, right? A small solar systems over here. So you can assume that we are sort of a pattern within a pattern within a pattern, right? So everything is following a certain pattern, and that's how basically the world, the universe is getting governed here, right? But again, it is not predict the future, right? Because we have multiple sort of predictions which can get true, right? So yeah, so he's saying what happens when this is the basically the first shell, right? This is the first shell here, and this is the second shell here, right? So if an electron basically goes from first to second shell, right? We want to give it energy, right? So if we let's say give it energy, if we let's say provide heat to the atom here, such that it has enough energy that it can basically bounce out, right? It wants to leave basically leave the first shell. So we want to provide energy to the atom over here to bounce, right? Let's say if the electron, this is the second shell over here, and this is the first shell here. If the electron basically comes from the second to the first shell, now it basically emits some radiation here, right? And this radiation can be in the spectrum of visible light, infrared light, okay, so on and so forth, depending upon the type of atom, right? So that's how it gives out energy. Okay. So you can think about this bouncing. Okay, this is pretty simple over here. It has no further details here. You learn about this detail in your A lab using chemistry classes, right? So this is just a brief discussion on how does it give out energy, right? Now we have ions over here. It is pretty simple. What are ions, right? Let's say we have an atom that is sodium, right? We have sodium 2311, right? And if I want to basically find out its number of protons, so what is the element? How does it look like? We have, let's say, element X. Okay, it has basically, let's say, this is A and this is basically Z here, right? So what is A over here? What is Z over here? Basically, A is the atomic number. That is how many number of protons are available in an electron of in an atom over here, right? And what is basically Z? It is the mass number, right? It is basically saying how many number of protons and neutrons are there combined together in the nucleus, right? So if I say we have sodium 1123, that means it has how many? What is the atomic number here? It is 11, and what is the mass number here? It is 23, right? So it means it has 11 protons. Okay. And if I basically talk about the atom over here, that is, it is not charged positively or negatively. So it will have a same number of electrons, right? And if I want to find the number of what is basically Z, Z is basically neutron number plus proton number, right? So we know proton number, we know Z. Can you find basically neutron number? Yes, we can find that out. So let's find the neutron number here, right? So it's going to be 23 equals to n plus proton number that is 11. So we have basically 12 neutrons inside the sodium element here. Okay, we have 12 neutrons here. Okay, so a normal atom which is basically has no charge like this. Okay, is called uh not an ion, by the way. Okay, it is just a neutral atom. It's called a neutral atom. Neutral means it has zero charge. Right, now let's see. Let me just draw its sort of structure here. This is sodium. So in the first shell, we will have two electrons, and then we will have eight electrons here, right? And then we have the last shell, which we have the 11th electron. So we have 2 plus 8, 10 plus 1, 11 electrons here, and inside the nucleus we have 11 protons and 12 neutrons. Right? So now let's say this electron is basically lost, right? To any other element doing any chemical bonding here. So it has basically less number of, it will have basically 11 proton numbers and 10 electrons here, because one basically has vanished, okay, somewhere. So now it has less number of electrons, okay. So it has less number of electrons and it has more number of protons. Overall, it has basically a positive charge, okay. So it becomes Na plus. Na plus means that it has plus one extra charge, okay. We basically assume that proton has plus one charge and electron has negative one charge, right? So if we add up the charges also, so we have plus 11 minus 10. So we have plus 1 overall charge of this element here, that is Na plus here, right? Let's say if it gains one more, it gains one more electron, right? It gains one more electron here. Let me keep it here. Okay. Now it will have what? It has the following scenario here. Now it has 11 protons. Now it has 12 electrons, right? So if I want to find the overall charge, that is going to be plus 11 minus 12. That is going to be negative 1 here, right? So it is going to be Na negative here, right? So this thing is called basically a cation. That is a positive ion. Okay, and this is called an ion, a negative ion, right? What is an ion? Ion is basically when an atom loses or gains electron, right? Okay. So this is a discussion on ions over here, and then we have nucleus here. Uh, ah, so there's a given example of hydrogen. So it is 1 1, right? So it has one proton, okay, one electron, and if you want to, and the mass number is basically 1. Want to find out the neutron number, it has 0 neutrons. Okay, 1 minus 1. The proton is basically containing only a proton in its nucleus, so it's a positively charged ion over here, right? Okay. Okay, so okay, they're saying something else over here. So they're saying what is a proton here? A proton is a hydrogen atom minus one electron, and that is a positive hydrogen ion, right? So if we have H plus, right, that means that this is the nucleus which contains only one proton, right? So if you talk about the actual hydrogen atom, it contains one basically electron here. If I take out this electron, it basically becomes H plus ion. That means that it has only the nucleus with a proton here. So that's a proton. Yeah, okay. So they're saying a proton is just basically a hydrogen ion which has lost one electron, right? So its charge is equal in size but opposite in sign that of electron, and its mass is about 2,000 times greater over here, right? So now this is basically summarizing charges and the masses of electron, proton, and neutrons. Okay. So the charge of proton is positive one, the charge of electron is negative one, the charge of neutron is neutral, right? And where it plays, protons and neutrons basically are in the nucleus, and electron are basically orbiting the nucleus, that is outside the nucleus here, right? The electron has a mass of one. Okay. We basically have a relative mass over here. The rest of them are basically 18. You can just learn this value here. Just learn 1840. The 1840 times heavier as compared to electron here. Okay. Electron is pretty light as compared to proton and neutron here. Okay. So these are the relative charges and the masses of the electron and the protons. These are not the actual masses. Okay. These are relative over here. Okay. Just basically there are benchmarks over here just to basically make you just learn the difference over here basically. Okay. This is the summary over here of different elements. Okay, if we have hydrogen, that is 1 1. Uh, how many protons, neutrons, and electrons are here? You can basically check it out. Okay, it's going to be easy. Then we have helium 4 2, right? And then we have lithium, that is 3 7. Then we have oxygen, that is 16 8. Then we have copper, that is 29. And 29 plus 34 is 59 63. ठीक है, so you can work out कि ये कैसे हैं सारे. Just pause the video and think about it. Now we have a standard definition over here of elements over here. So we have X, C, A. इन लोगों ने इसको उल्टा कर दिया है. ठीक है. So मैंने इसको basically ऐसे explain किया था आपको. कि we have Z here, we have A here, right? So in their context, basically they have flipped the variables here. They have made this as A and this as Z here. ठीक है. So it's same, right? So just learn that the bottom one is basically the proton number here. ठीक है. That is equals to the number of protons and number of electrons. ठीक है. In a neutral atom. And what is A here? In this particular definition of your book, it is basically the mass number here. That is number of protons plus number of neutrons. ठीक है. Okay, Ji. Then we have isotopes here. So this is just introducing you basic terms here. If you haven't taken chemistry over here, you know the basic terms here, right? So what are isotopes and nuclides here? Okay, so isotopes are what? These are the elements which have the same number of electrons and protons, but different number of neutrons, right? So this is the definition over here which you should learn by heart. So these are elements of basically these are atoms of the same element which have the same number of protons but different number of neutrons here. Right? Let's say we have isotopes of hydrogen. Okay? We have 1 1, that is hydrogen. Then we have deuterium. Okay? And we have basically tritium here. Right? You can see that in case proton number is same, right? It's 1 1 1. However, their number of neutrons are changing here, right? Okay? So the first one has basically 0 neutrons. The second one has one proton, one neutron here, and the third one basically have two neutrons here. They have the same chemical properties, okay, but their number of neutrons are different here. They are both right. So the proton numbers are the same, but not their nucleon numbers, right? So nucleon numbers क्या होते हैं हमारे पास? These are all nucleon numbers. Okay, these are called nucleon or mass numbers. Okay. An element can have more than one type of isotope. You can see that hydrogen has three isotopes here. Okay. Then there might be a question, okay, sir, why do we always use this? Why do we see this in the periodic table? Because these are present in the atmosphere basically in a certain proportion. Okay. Let's say hydrogen 1 1 is basically 68% in the air. Hydrogen deuterium is basically, let's say we have 12% here. And then we have 30%, let's say tritium here. Right? So the major proportion of which is present in the air is basically present in your periodic table, right? Each element form a nuclide, right? That is this. This is the combined thing is called a nuclide here, right? It contains neutrons, protons, electrons combined together, right? Right? Nuclide with the same number Z but different number A isotopes. Radioactive isotopes are termed radioisotopes or radionuclides here, okay, because their red nuclei are unstable, right? So what are radioactive elements? We'll learn in a while. Okay, if you have a radioactive isotope, it basically emits some radiations, right? They emit radiations. ठीक है, and if they emit radiation, obviously their mass will be reduced. ठीक है, so they basically lose their mass, right? ठीक है, and these radiations are always harmful over here. They can be alpha, beta, gamma, depending upon the type of the radioactive element over here which is getting used in the experiment. Then we have a question here which is pretty simple here. I'm going to leave this as a homework assignment here. ठीक है, it's pretty simple. So just pause the video and solve the question here. ठीक है. These are three isotopes here. You want to find the proton numbers, the nucleons, okay, what is the mass number, and the neutrons in each isotope over here. You will realize okay, the number of neutrons are changing, but the proton number is same. That is why they are isotopes, right? Then we have a nuclear fission process over here, right? So it's pretty simple. Just imagine this: that you have a daughter, basically mother element here. What is nuclear fission? Is basically as follows. Okay, you have sort of you can say a measure the mother element here. Okay, that is starting the process, and then what happens as you basically start the process. Let me just put my charger. So if this process starts, basically it splits itself into two equal parts. Okay, it becomes half, almost half. Then it basically the chain reaction. Chain reaction means it goes, it continuously carries on unless you basically stop it using some method over here, right? Becomes further half, right? And so on and so forth. So this splitting of the element into its daughter elements, okay, is called fission here, right? Okay, these are the daughter elements. Okay. So what is the content saying over here? The heavy metal uranium is a mixture of isotopes of uranium 92 235, that is this 92 235, right? Called uranium 235, which is basically very important over here because it is widely used in this process here, right? So when the process basically takes place, it basically starts to divide itself into two equal parts. And what does it also produce? It produces a huge amount of energy. Okay. So that energy is also used in current world to produce electricity. Okay. So that is basically used in nuclear reactors, right? So we have nuclear energy that is producing electricity also. So that is what is used in that particular power plant. Okay. Some atoms basically decay quite naturally, emitting high-speed neutrons, right? So if one of this hits the nucleus of the neighboring uranium-235 atoms, okay, it again starts to break into two equal radioactive nuclei and barium, krypton, and so on and so forth, right? So in fusion, neutrons split at the uranium-235 nuclei, a chain reaction is set up, okay? This is basically what happens over here, okay? So you have basically we hit the uranium-235 atom initially with a neutron gun, right? What is a neutron gun? It basically emits a neutron here. As soon as it basically hits this, it makes the nucleus more unstable, starts breaking down. Okay? It produces basically what? Two daughter elements, okay? And then some extra neutrons. These neutrons hit the neighboring uranium 235 atoms over here, and then they start to break down. Okay? And this basically continues on and on and on, okay? Till we basically stop this using a method that is called basically you can use boron rods to basically stop absorb the neutrons. It basically stops if we have no further neutrons available, and then we can easily stop the process to further continue here, right? Otherwise it will keep on going on and will have huge amount of energy produced, and this can also lead to explosions, right? This is how it is used in a nuclear reactor. Okay, it's a nuclear reactor which basically produces electricity. Okay, so what happens over here, you can see we have some control rods here, right? These are made up of boron, right? Boron is good at absorbing, it absorbs basically neutrons, right? And then we have uranium rod here, right? That basically carries out fission. It carries out fission, right? Which gets broken down to two equal parts, so on and so forth. And this is a graphite core, okay? It is made up of basically carbon, right? It is pretty good for it is strong material which basically does not allow it basically creates a very strong rigid structure over here, right? So how does this basically thing works? So we have a fission happening over here, right? So what does it do? It basically let's imagine कि हमने इसको neutrons hit कर दिया. The process starts, right? This process starts over here. It produces also huge amount of energy, right? Heat. So what happens over here is this heat energy is basically going from a pipe. This goes through a heat exchanger over here, and we are basically providing cold water in the pipes here. So what is happening over here? This cold pipes are basically getting heated up using the hot steam that is produced by the fission process here, right? And then this is basically the outlet here, right? So this outlet is producing high pressure, very high temperature steam, which goes to basically a turbine, right? And this goes to a generator over here, ठीक है? Which basically produces what? Electricity, right? So this is how this thing works over here. If it does not make sense, you can pause the video and go back and rewatch this, right? If you have further questions, you can drop me a text, or you can drop a message on the group and tag the T here, right? Then we have finally nuclear fission over here, right? What is nuclear fusion here? Just it's the opposite of nuclear fission here, right? In nuclear fission, we're dividing the the main element into daughter elements over here. Now, if we reverse the process, if you combine two elements together to produce a heavy element, that basically is nuclear fission here, right? Now, obviously, if you want to combine two elements together, you would need huge amount of energy, right? You have to provide energy over here, right? So it's not possible on Earth over here. Okay? So you cannot create this manually using some machines here because it needs huge amount of energy. Right? So this process is basically happening on the sun, right? How is sun producing energy? Using fission, right? So what is happening over there? Two hydrogen elements are combined together to form helium, and then two helium are combined together to form other elements here. Okay. So if what is nuclear fission over here? So if we have two smaller nuclei combined together to form a bigger nuclei plus heat energy, right? So this process is called basically what? Nuclear fission over here, right? If light nuclei join together to make a heavier ones, this can also lead to the release of energy here, right? Such a fusion reaction has been achieved in the hydrogen bomb here, right? So we have done this, but it was not a good attempt here. This was just a hydrogen bomb, right? which was dropped at Hiroshima and Nagasaki in World War II. Okay, so it was under experimental stage. So they tested on the humans. There was not a good output, right? So again, still the Hiroshima and Nagasaki are radioactive, right? So fusion can occur if the reacting nuclei have enough energy to overcome their mutual electrostatic repulsion here, right? Obviously, when you want to bring two nucleus together, right, you will have to give in energy, right? Huge amount of energy because they have electrostatic repulsion, right? Which is going to repel them. But if you want to still bring them together, you have to give huge amount of energy. That can basically cause them to break the electrostatic forces and combine together, right? So this can happen if we have raised to a very high temperature, that is around 100 million Celsius. Okay, that is not attainable over here. So they collide at very high speeds and then they basically merge together to form a heavy element over here. Okay. If energy is released, okay, it is enough to basically carry out this process in a chain. Okay. This is basically called thermonuclear fusion over here. So what where can you find this? Practically, it's basically happening at the sun, right? So sun's energy is getting produced from nuclear fusion here, right? The huge amount of energy that is reaching all the planets around the solar system is basically produced with fusion here, right? So the temperature at sun is high enough to for the conversion of hydrogen into helium to occur in a sequence of thermonuclear fusion reaction known as hydrogen burning sequence. Right? Again, they are saying ki how are new elements getting formed? Basically, we fuse them together. When the Big Bang occurred, when the universe was born, so what happened is basically the temperature was extremely high. So it was enough to basically start the nuclear fusion, and it basically started. It formed different planets, solar systems, stars, so on and so forth. And now you have the universe, which you can see through NASA website if you want to explore here what is happening over here. We also have an app that is NASA Earth. You can literally see Earth in basically live mode. How is the Earth looking right now, right?